Today we are building a boost converter out of a 555 timer, MOSFET and LM741 comparator. As you can see in this setup, there's a 12 volt input and a 24 volt output. Zooming in onto the 555 timer, you can see that R1, R2 and C1, C2 are actually the determinants of the frequency of the 555 timer. The diode is to ensure that the transistor is not shorted. Meanwhile, the comparator is based on a reference voltage with a Zener diode IN4736A and a live feed on the output line that allows you to compare your output voltage together with your reference voltage. The load is located over here and labelled as R1. In this diagram, the load is a 1000 kilo ohm load, but in our actual experiment, it will be using LEDs. So what you see in this diagram is exactly what we have shown you in the previous schematic. The first chip on the left is your 555 timer. The MOSFET is the one with the heatsink, and the last chip on the right is your comparator, LM741. Most of the capacitors here are used to smoothen out the voltage. You can see the Zener diode is the diode over here, which serves as a reference voltage for the comparator. Our LEDs are all here. There are 14 of them, and if we remove the light, we can see that they're actually lit up. Input voltage is 12 volts and pumping out 0.06 amps. So this is nice. We will be taking a voltage reading now. So right now we have the entire setup. As you can see, the output voltage reading is 24.3 volts, which is almost what we want. This is the output load, and this is the input power. By tuning the potentiometer on the right, we can change the voltage. And in order to measure the output power, we've used this multimeter as an ammeter by arranging it in series with the load. As you can see, the output current is approximately 0.02 amperes. Right now we'll be showing how our through-hole PCB will step up a 12 volt input into a 24 volt output. As you can see, by tuning the potentiometer, we can control the output voltage. So right now at 24 volts, 12 volt input, 0.048 amperes, we can light up about 13 LEDs. We will now conduct the test for saturation on the inductor in this boost converter. As you can see, the starting inductance is 143 microhenries. By changing the current flowing through the inductor, you can see that the inductance begins to change. And this is specifically a drop in inductance. This only occurs in the saturation region, and it's not supposed to occur if the inductor is not saturated. A saturated inductor will cause power loss because additional current input will not result in current output through the inductor. At our required input voltage of 12 volts, the inductance has dropped from 143 microhenries to 8.33.